And here's the example. The formula for this function is f of xy equals x cubed plus xy squared plus 3y minus 10x plus 150. Okay, you've already read and worked on some problems from section 14.1, so what I'm about to do shouldn't be too unfamiliar to you. There's two main ways to plot a function like this. And in Mathematica, the first way to visualize it is with plot 3D. So once I've got the function entered, I can put it into plot 3D like this to make a plot of it in three-dimensional space. How is this plot generated? What does it mean? You imagine the xy plane as being horizontal, okay? And then you imagine picking points in that xy plane, plugging them into the function. For example, we can plug in the point 2, 3 to get an output, 165 in that case. And then the corresponding point in 3 dimensions, whose coordinates are 2, 3, and 165, is going to be a point on the graph. So it's going to be 165 units above the xy plane. And I can do that for every point in the plane. Find some nice way of connecting all the points. Plot 3D does that, and it produces a graph that looks like this. Remember, the positive x-axis goes to the right, the positive y-axis goes into the screen, the positive z-axis goes upward. It does appear, if you move this graph around a bit, that there is a local max and a local min. A local max somewhere right around there, and a local min somewhere right around there. Actually, it's not completely clear to me that it doesn't go all the way down to 0 and maybe even negative. So I might actually need to change the point a little bit to make sure it doesn't go negative, because density shouldn't be negative. That's why I added the 150. And it is representing a density. F of 2, 3, I'm imagining it is representing a density at least. So this imaginary application. F of 2, 3 is 165. What does that mean? Well, let's pretend we've got some units. Let's pretend the mass units are in grams, and the area units for a thin plate of metal are in square centimeters. I'm graphing it over this box, this square, where x goes between -5 and 5, and so does y. So a square that looks about like this is the window I'm plotting it over. And effectively, I could imagine restricting my domain to being that square instead of all of the entire plane. And effectively, I am going to do that actually. So I'm imagining that this is a thin sheet of metal. Okay? And the distance units are in centimeters and mass units are in grams. And therefore, as a density, this would be in grams per square centimeter. Not cubic centimeter, because I'm thinking of it as a thin sheet of metal. I don't have to worry about the thickness. What does the fact that this is 165 mean? 165 grams per square centimeter. It means if you go to the point whose coordinates are 2, 3, right about there, and you get some scissors out, cut out a little small piece of the thin plate right there, what will its mass be, approximately? It'll be the density times the area that you cut out, approximately. It's not perfect, because this is a density just at one point. But if this square that you cut out is small enough, because the density function here is continuous, its value is not going to change very much over the entire little tiny square there. And you can get a good approximation for the mass of that by multiplying that times the area. So for example, if the square you cut out has side lengths equal to 0.1 centimeters, so that the area is 0.1 centimeters squared, 0.01 square centimeters, You multiply that times 165, you'll get an approximation of the mass of that little chunk there. So your approximate mass is going to be 165 times 0.01 units in there, grams per square centimeter, times 0.01 square centimeters. The square centimeters will cancel, giving you 1.65 grams, which seems reasonable, I guess, but it might have that mass. That's the idea of what the density means. Okay, it gives you, helps you find approximations to masses near any point. You cut out small regions of the plate. What's the other way to visualize functions like this? This was on the homework a lot. Anybody want to say it? Contour maps. Maps of level curves where the function is constant. In Mathematica, with functions like this, you can use ContourPlot to do that. Don't set f of xy equal to any specific number. Just type it in there as an f of xy. There we go, there's a contour map. Kind of pretty. You can make it more informative by adding even more contours. The default, believe it or not, is 10. Make it even 15, you can add some. Oh, let's make it much bigger, let's say 50. That's more informative. These curves are called level curves. They are curves along which the function, the density in this case, is constant. And actually, if you put your cursor over those curves, you can see the constant value. Along that curve, for all points on that curve, the density is 156.4 grams per square centimeter. So you take any point along that curve and cut out a little tiny area near that point. The mass of that region will be 156.4 times the area of the little chunk that you cut out. Darker shading corresponds to lower values. Lighter shading corresponds to higher values of the function, which again in this case is the density. So the highest value seems like it's going to be in there. That's where the shading is highest. Well, okay, it's a local maximum. The shading gets lighter over here. So the true highest value overall is going to be somewhere along this edge, it looks like. Lower values correspond to darker shading. You're going to have a local minimum there for the density. But the overall density is going to be lowest. It appears perhaps right there. Is it going to go negative? I should probably check that. I don't want it to go negative, so we may need to modify this function. F of -5, 0 is going to probably be the lowest value, it looks like. And that does not go negative. 75, that seems like a strange way to look at this graph. X is -5. Oh, okay, I'm thinking about it wrong. It's going to be lowest, it looks like more toward the upper left and lower right corners. Yeah, ours wrong in my thinking. Sorry about that. Upper left and lower right corners, where you don't see any curves there, it appears it's going to be lower. You just don't see them. Okay, I did draw them. So I should instead calculate something like f of -5, comma 5. It does go negative, so I need to change. Let's see if it's symmetric with respect to y. -65, that's probably the lowest value. So I need to make this 150 plus 65, 215 exact at least. Play it safe, maybe I do a 250. Which makes this calculation wrong now. Instead, it should be 2.65 grams instead of 1.65 grams. Let's use the 250 now. Okay? That way we make sure the density never goes negative. Okay, well, how are you going to find those local maxes and local minimums? You might be interested in those too. Got a guess? Use Calc 1 and Calc 2? Calc 1 even? Take derivatives, yeah. Find critical points. Maybe use some sort of second derivative test. And that is what you do. Except now, because this function involves more than one independent variable, they're not ordinary derivatives, they're called partial derivatives. Because they partially differentiate the function, so to speak. There's lots of notation here that can be used. The notation I'm going to show you today is this notation. That's the partial derivative of z with respect to x. What's this thing? 2 spots. Well, that's sort of a fancy looking d. Strange looking d. Should you call it d? Some people do. Some people look at this and they say dz dx. Other people, because it doesn't look like a d too much, say partial z, partial x. They sort of think of that as a partial differentiation operator, and they put the word partial in there. Either way of saying it to me is okay. It is a partial derivative because that function depends on more than one independent variable. And I will use this notation for it. But whether you call it dz dx or partial z, partial x, or partial of z with respect to x, you can use any of those terms. How do you calculate it? Well, technically speaking, we need to use limits. We need to use limits. Okay, it is in the book. There is a discussion about limits in the book, and you do have a few problems related to that, completion problems. But for the most part, you're not going to worry about limits, right? There's always this game in calculus. Everything is based on limits, but in the end, you don't have to worry about them typically. Okay? There's these good facts like the chain rule, the product rule, the quotient rule, etc. Facts about derivatives that you can use without using limits. But everything is based on limits, and you should know that. Anyway, as far as calculating partial derivative of z with respect to x, you just look at that expression and treat the y like a constant. That's all you have to do. Differentiate it with respect to x. So differentiating that is going to give you a 3x squared. Differentiating this with respect to x, treat the y squared like a constant, like 10 or something. The derivative of 10x would be 10. The derivative of y squared times x is y squared. 0, 0, minus 10. So we're going to get 3x squared plus y squared minus 10 is the partial of z with respect to x. But there's also a partial of z with respect to y. dz dy. Treat the x like a constant then. The derivative of that will be 0. Treat the x like a constant. The derivative of this will be 2xy, yeah, we're going to do it on the front. 2xy, 3, 0, 0. So we get 2xy plus 3. To find critical points, you need to set both partial derivatives equal to 0 and solve the resulting system of algebra equations. Set that equal to 0, set this equal to 0, solve for x and y. Evidently, there are 2 solutions. There's 2 critical points that we can see there in the picture. Probably the best way to do this is to take the second equation and solve for y as a function of x. Plug it back into the first equation so that you have only x's. And hopefully, perhaps the quadratic formula or something will be helpful at that point. Maybe not. Let's see what happens here. If we subtract 3 from both sides here, get this, then divide both sides by 2x. As long as x is not 0, the critical point is going to have to satisfy that equation. Here, this can be plugged in here for y. Oh, we're probably going to end up with a fourth degree equation, although we might still be able to use the quadratic formula for it. 3x squared plus 9 over 4 x squared, when I squared negative 3 over 2x. Minus 10 equals 0. Multiply everything by x squared to get 3x to the fourth plus minus 10x squared plus 9 fourths. You can use the quadratic formula to solve for x squared here because this is a quadratic in x squared. X to the fourth is x squared squared. So when you do that, you get x squared is 10, the opposite of that one, plus or minus the square root. That squared is 100, minus 4 times 3 times 9 fourths. 4 times 9 fourths is 9. 9 times 3 is 27. Over 2a, that'll be 2 times 3 is 6. 5/3 plus or minus square root of 73 over 6. Double check my work here. Square root of 73 is going to be between 8 and 9. 5/3 is 1.6 repeating. 8 over 6 is 4/3, 1.3 repeating. 9/6 is 1.5. It looks like the plus or minus will work here to give you a positive number here. Then you can take the square root, plus or minus square root of that to get the x's. And actually, that's making me realize there's actually 4 critical points. I realized that first. I should have realized. Actually, going to be a critical point right about there. Another one right about there. This one's going to be a local max. This is going to be a local min. These 2 critical points are going to be neither. They're called saddle points. They're saddle points because if you look at the 3-dimensional graph, it looks like a saddle. You can actually see it. Okay? It'll be going like this in one direction and like that in the other direction. It'll look like an actual saddle when you zoom in close to it. I think before I put this on Moodle, I'll go ahead and do that, but we're out of time for the moment. We'll see you on Friday.